I'll get started with lecture 5 today. Lecture 5 today will continue covering the calculus of variations, part 2. And I am in chapter 4 of my book, and we're going to start going a little bit deeper into calculus of variations. We'd only touched the surface, and what we're trying to do, what are we trying to do? A lot of physical problems in many different areas of expertise: fluid mechanics, structures, thermal, and even light travel, or even navigation. They all can rely quite a bit on calculus of variations. In fact, it can be even used for image processing. You can have a horrible image, and you can use calculus of variation to optimize the image. And what I had discussed in the previous lecture is that what I'm trying to do, as an example, here I have a chain, a hanging chain. And obviously, the red curve is not the curve that produces, that red curve does not produce, it's not representative of a hanging chain, of course. The hanging chain is really that chain in metal that you can see. And so I'm trying to find the shape of that chain, right? And what we talked about was, in essence, if I have a chain that's hanging at 2 points, I know the exact shape. I know it's going to be this one here. And so I know that's a real solution. And what I want to know, you know, what is that chain shape? And I'm making that assumption. I'm making the assumption that it has a shape, which is true. But the real solution to the problem is yx, and I'm going to assume that maybe it's a different shape, which probably doesn't even make sense to you. That's fine. We call this y tilde x. This is a real one, and this is the virtual function that I've created. And so what we talked about is that I am looking at curves near y of x to really understand how to find that function that minimizes the functional. And the functional we discussed is going to look like a functional, which is a function of yx of x. And we talked about how I'm looking for this function that minimizes this functional. That's what we're trying to do. And this could be the integral from x1 to x2, where the domain is given by x1 and x2. And this functional is going to depend on this integrand, which may have y prime as an example of x dx. And I'm trying to find this function y that minimizes I. That's my goal. And so what we talked about is considering this virtual function, and let's consider that difference between the virtual function and the real function. And I'm going to consider the difference to be eta epsilon eta x, which is del y, which is y tilde of x minus y of x. That's what we discussed. And we also discussed that these endpoints, at these endpoints, we have a situation where eta x, in this case, is 0, because obviously y tilde and y coincide perfectly. You can see that there. It coincides perfectly. And so for that reason, we then talked about how eta has to be admissible, has to be smooth, has to be continuous. And when I say smooth, it needs to be sufficiently differentiable. And epsilon is an infinitesimal scalar quantity. That's what we discussed. And so what is my goal? My goal is to then substitute this y tilde in here. And when I do that, I end up with this expression, I tilde, y tilde of x equals the integral from x1 to x2, f tilde, y tilde prime, x dx. So that's what I get. And so what I want to do now, I notice how now I tilde is actually now a function of epsilon. And so all I have to do now is to use Taylor series expansion about epsilon equals 0, because I want epsilon to be close to 0. When epsilon tends to 0, the virtual function becomes the real function. And I want that. I want that to happen. So I want to examine the family of curves near the real solution, because if I can do that, then I am in better shape. Okay? So, and so, what I want to do is to make this virtual function, I want that to be close to that real function. That's really what I want. And so I want to do a Taylor series expansion about epsilon. And what we discussed is that we can do that very simply as this. And then I'll take the derivative of I tilde with respect to epsilon and set that equal to 0 times epsilon. So this is just Taylor series expansion. You've seen this before. The second derivative of I tilde epsilon at epsilon equals 0 and 1/2 epsilon squared plus etc. And I know what I tilde at epsilon equals 0 is. I know what this is. This right here, when I set epsilon equals 0, what happens here when I put epsilon equals 0? When I put epsilon equals 0, what happens there? This becomes 0 and y tilde becomes y. So then I recover all these y tildes become y. This y tilde prime becomes y prime. F tilde becomes f. Everything becomes I. So here, this becomes I. And I want I tilde to be equal to I. And for that to happen, I have to set the dominant term, the first version of I, which I call that the first version of I, to be equal to 0. And then I have to set, and then to determine whether it is a minimum or maximum, I have to examine the condition, this condition here. It is greater or less than 0. So that is what I want to do, right? Secondly, what I want to do then is to calculate what this looks like. Okay, and we did that in the previous lecture, and I will do it again. So the first version of I is the derivative of I, where I have replaced y with y tilde. And so therefore I have this y plus epsilon eta d epsilon at epsilon equals 0 times epsilon, d is equal to 0. And then I can now conduct that derivative. And we did that, right? So that's equal to the integral from x1 to x2. And the derivative of what's in there, which is partial of f tilde respect to y tilde, and partial y tilde respect to epsilon, plus partial of f tilde respect to y tilde prime, and then now what I notice very quickly is that these guys right here, the derivative of y tilde respect to epsilon is really eta of x, and this is eta prime of x. And this is evaluated at epsilon equals 0, dx times epsilon equals 0. And you can see here that when I set epsilon equals 0, this f tilde goes away, becomes f, y tilde becomes y, everything becomes the original function. So I get the integral from x1 to x2, and I get partial of f respect to y. And then this eta times epsilon becomes exactly this del y right here. So I get del y dx equals 0. And then I showed you how to integrate by parts. And when I integrate by parts, I can then remove this prime out of here, so I can then combine with this term. So that's what we discussed, and we were successful. We were able to find the Euler-Lagrange equation that allowed us to then, when we solve that equation, that function y is the one that minimizes the function. I believe this is a mathematical miracle, in my opinion. It is quite incredible. And in fact, I think it is quite amazing, actually, to be able to do that. And last week we covered, in the previous lecture, I'm sorry, we covered what will happen if I'm trying to find a straight line, and I found a straight line. It was not by coincidence, we did it. And so then I showed you how to integrate by parts. We're gonna put this term here on the left side. We're gonna put this term here on the right side. And then I'm going to remove the prime once and put it at the bottom. I'm gonna transfer that prime over, so it's like this. And I'm gonna cross plus and minus. The bottom term here goes back into the integral. And I'm trying to do is integrate by parts. There's many ways to do that. That's the way I teach it, but it doesn't mean that you're stuck to the way I do it. You can do it your own way. So I don't want anybody here to feel that they're stuck on a particular approach. And so then I get the integral from x1, x2, partial of f respect to y, del y, and now I have the minus of derivative of f respect to y. And you can see here, sorry about that. You can see here that I'm going to take this term right here. This term right here at the bottom will be multiplied. So I get this. And then I have the boundary term. And there's a plus sign right here. So I want to keep track of that. There's a plus sign right there. So this multiplication times that is what I want. So that's the derivative of f respect to y prime del y evaluated at x1 and x2, the endpoints. So this is your boundary term. And what is a boundary term? So my curve for the hanging chain, this is my boundary term in 1D, right? At x1 and x2, that's my boundary term. And then this term right here is in between. That's the integral between those endpoints. So very important. And then, so this is equal to 0. And you can see I've done everything correctly. I've transcribed everything correctly, but not quite, because what I can do now, I can factor this del y. You can see that. So let me just do that now, so I don't have to repeat myself. And then I'll use a fundamental lemma of calculus of variations. And for any arbitrary del y, because del y is not equal to 0, I'm varying this distance over this whole domain. Over the whole domain, I'm trying to vary that. So clearly, del y is not 0, del y is arbitrary in our case. And so as a consequence, the fundamental lemma of calculus variation tells you that if the integral of phi of x, gamma x, dx is 0, and this is arbitrary, then phi x must be equal to 0. And you have to invoke, every time you do problems, you have to invoke this every time. And so that's called the Euler, they give it a name, so it's the Euler-Lagrange equation. And the Euler-Lagrange equation is the partial of f respect to y minus partial of f respect to y prime equal to 0. And this is valid, be very careful. This is valid between x1 and x2 with the following boundary conditions. You have two conditions. You have the natural boundary conditions and the essential boundary conditions. There's only two choices here. Either this is 0, that's one option, and I'll call that a natural boundary condition. Or the other option is for y to be known. Y is specified at that boundary. That's at x1. At x2, the same thing. Derivative of f respect to y prime equals 0, or y is specified. So you have two options here for each endpoint. So in our case, we did specify how the chain is going to hang. We told it exactly how it's going to hang. And so I know what y that is. I know what y that is because I specified it. So as a consequence, in our case, you want to do a rectangle to specify that all the boundary conditions are essential. But if I had not specified, the y here somehow, I left it free, then at x equals x2, then this must be true. This must be true and not that one. And I'll cover an example coming up on that. So, let's cover some questions that we have as a team. The first question is, here I have the phi x and gamma x. And the question is, how does this relate to the equation here above? And so here, gamma of x is del y. And the fundamental lemma of calculus derivation tells you for any del y, for any arbitrary value of del y, that phi of x must be equal to 0. In our case, phi of x is the integrand, which is not the part that's del y. So just this part. And so that'll be that question. And the second question we have is why my Taylor series expansion is not about x. And the reason it's not about x is because that will be a different problem. That will be trying to find the minimum of a function, a regular function of x. So if I have a regular function x, which is 3x squared minus 4, my Taylor series expansion is about x. But now that's not my situation. My situation is I'm trying to find a function y that minimizes I. And I considered a family of functions near the real solution y, which I call y tilde. Okay. And that y tilde minus y, I made it equal to epsilon eta x. So now that difference really depends on epsilon and this eta function. And so I did Taylor series expansion about epsilon, which means that my Taylor series expansion has to be about epsilon. So I shouldn't be taking derivatives with respect to x because I'm not doing a Taylor series expansion about x. I'm doing a Taylor series expansion about epsilon instead. Okay. And so that's why we're not taking derivatives with respect to x here. The third question that's coming up right now that we would like to cover is what is going on here? So you either have, if I have a situation of a times b equals 0, either a is 0 or b is 0. And in our situation, when I look at my boundary conditions, a will be the derivative of f respect to y prime, that will be your a, and either that's 0 or your other options for b to be 0, which is del y. Well, if del y is 0, then y must be specified. Y has to be specified for that to happen because If y, del y is 0, that means that the y tilde and y are coincident. They're coincident. So del y is 0 as a consequence. Has to be. So if I specify the value of y, I want y tilde to go right through it. And that's why I will write y specified. You don't write that del y is 0. That's incorrect. The correct answer is to say that y is specified. And so there's two options, and you have to circle the correct option for every physical problem that's discussed. And then the fourth question we got was, what is the physical significance of natural versus essential? And I'll be covering that later on as I cover physical problems. So let's cover an example in my book and in my notes. So if I have a functional I, and not function, a functional I, which is a function of y of x, and it's a mathematical problem. There's no physical significance to this problem, but I created this problem on purpose because it has some interesting aspects. X squared plus 2x, y prime squared plus 10xy, and then dx. And I want to find what function, there's a question, what function f y of x minimizes the functional I. So that is a question that we have. Okay. And so how do I go about that? I will find the first variation of I and set that equal to 0. I already know how to do that. So di tilde d epsilon at epsilon equals 0 times epsilon. And so then I'll take the derivative of this. Sorry about that. And I'll continue here with y prime plus epsilon eta prime, if you recall, plus 10x, and then y plus epsilon eta dx. Okay, so I'm trying to find that derivative. And once I do that derivative, I will set this to epsilon equals 0. And times epsilon times this equal to 0. So that's the process I want to use. And so here now, I will find that derivative. And you can see here, this does not depend on epsilon. And this does not depend on epsilon. This depends on epsilon. This does not depend on epsilon. But this depends on epsilon. So when I take that derivative, all I get is this. I get this, x1, x2. And I will get 2x eta prime. And I actually have a mistake because there's a square here. So I need to be careful there. So when I find that derivative is, right, there's a square there. I'm sorry about that. So when I take that derivative, I get y prime plus epsilon eta prime. And then I apply the chain rule to that. So I get eta prime. So again, I have a mistake. This 2 here, derivative of that complete thing is twice. And then I have the inside derivative of that, which is eta prime. And then here, the only term I have that survives is that one, plus 10x eta and dx. And then set this equal to epsilon 0 times epsilon and set this equal to 0. So that's what I have. And now I have to set epsilon equal to 0. So this term goes away. And I can now multiply epsilon back in there. So then I get the integral of x1, x2, 2x, y prime, and del prime, eta prime times epsilon is del y prime. And eta times epsilon is del y. Recall that this is y tilde prime minus y, or the distance between the two curves. And this here is y tilde minus y. So don't forget that. And so then I have here 4, because 2 times 2 is 4, 4xy prime, right? And that's del y prime plus 10x del y dx equal to 0. Okay, and now I have to resolve, now I have to take care of this prime. I don't want that prime there. I want to integrate by parts now, and I'll just do that now. So I have 4x, and let me just do that in a more spacious location. So 4xy prime del y prime. So I've taken this term right here, put on the left side, and this term on the right side. And so then I can integrate by parts. So I get 4xy prime del y plus minus, so I've removed the prime once and I move the prime over. That's how I integrate by parts. Doesn't mean that you have to do it the same way, okay? And so now I can write everything here, x1, x2. And I get this term at the bottom, the one at the bottom, this times that goes back into the integral. At least that's the way I learned how to do it. And you're entitled to do it anywhere, any other ways, okay. Plus 10x, and then I'll factor the del y out because there's a del y out here and there's a del y here, so I'll just factor it out. Dx, and I have this boundary term, this cross term here. So that becomes plus 4xy prime and del y x1 and x2, and that's equal to 0. And independently, this term here and this term here independently have to go to 0. So in other words, what I have now is the next step, which is to use the fundamental of calculus of variations. And for any del y that I have, then I have my Euler-Lagrange equation. And just look at the Euler-Lagrange equation together. This is the one. This one here in parentheses. Because for any del y, this whole integral has to be equal to 0. So this must be equal to 0. And so then I have minus 4xy prime plus 10x equal to 0. And that's true between x1 and x2. And the boundary condition is, if you recall, I have this boundary condition here, and I have basically a times b situation. So a times b has to be equal to 0 at each end point. So either this is 0 or that's 0. And so that boundary conditions then become, and then you will write it in this manner. You'll say natural and essential. And then you'll say, okay, at x1 and at x2. And so at x equals x1, I either have this equal to 0, or y is specified. 4xy prime is 0 here at this boundary, or y is specified. And so this, and then you will select the boundary conditions depending upon the situation. Okay, so that's how we learn how to do it, and I hope that is quite clear. What are we trying to accomplish? And you're not allowed to use this equation straight out. You're not allowed to use this equation ever. You're not allowed to do that. But you're allowed to do it the way I'm doing it here. There's one way to do it. The second way to do it is more straightforward. So I have I equals x1, x2, 3x squared plus 2xy prime squared plus 10xy dx. And I want to find the function. By the way, if I solve this for y, this function y is the one that minimizes I, meaning if I choose any other function, if I were to choose any other function y, and I just plugged it in there, I would be a number greater than if I were to substitute the real solution to this governing equation. Very powerful idea, okay? It could either minimize or maximize. I actually don't know which one it is because I didn't examine. I had to examine the second version of I to figure that out. And I didn't do that. But the quicker way to find the first version of I, if you're interested, is just call this F and notice how F depends on Y and Y prime dx. So you're going to find, you're going to then expand like this, derivative of f respect to y del y plus the derivative of f respect to y prime del y prime, and then you have dx equals 0. You're allowed to do this, but later on when I ask you to do the problem two ways, Taylor series expansion, or this way, you have to do it with these epsilons, and if I ask you to just take the variation of I, you can just do this. This will give you the same answer. You know, if I just take the derivative of this with respect to y, this is the only term that has y, so that's 10x del y plus the derivative of f with respect to y prime. The only thing that has y prime is this one, so that's 4x y prime del y prime, right? So that's that, and this is that. And I quickly got to the answer. And this right here is exact same thing I found. I found that here. You can see that here. Sorry, guys. Let me clean this up so it's clear what I'm talking about. You can see that there. Same thing I got earlier. So this right here is the same thing I got earlier. So that's another approach you can use, but it's less robust because if I want to find the second variation of I, for example, then it will become more complicated. So using epsilon is actually quite valuable. So the first question that came up is, you know, why I am not taking a partial respect to x del x. I am doing it for everything else. And the reason is because I'm doing a variation about in the height direction. So in other words, the del y we're discussing is this height here, not in this direction. This direction is del x. I'm not doing that variation. That variation is not what we're talking about. Instead, we're talking about the variation in the height direction. And that only involves del y and not del x. The second question that came up is my notation of I with the brackets with y of x, and maybe I have even y prime of x, or maybe I have w comma x. And the reasons we use this bracket is to denote that this is a functional. Secondly, I am also talking about what are the this tells me what functions are the ones I need to consider that are the ones I'm going to find to then minimize or maximize this functional. So this is just helping me determining that. And these ones here, what that helps me to understand is what are the spatial quantities of interest, whether it's x1, x2, whatever it is. So, okay, so now what I want to do is study an interesting problem, which is actually a physical problem that will be discussed much later. And it's a beam, and this beam is resting on an elastic foundation. And that elastic foundation is this one right here. and I have a distributed load applied Q, and I want to figure out what deflection W minimizes my functional I, or you could even maximize it, one of the two, right? And so in this beam problem, it is fixed on the left side so that the slope in this end is 0, and also the slope is 0. So not only the deflection is 0, but the slope is 0. And so that is the question that's been asked. And so what we want to do then is to find the functions W that will minimize or maximize I. And to do that, again, I'll find the first variation of I and set it equal to 0. And to do that, I had to find the first variation of I. So I had to find the first derivative of I tilde respect to epsilon and set epsilon equal to 0 times epsilon, and that is equal to 0. So this is equal to the integral of x1 to x2. And then the derivative of this expression like that. And I'll substitute for W. For W, anytime I have W, I'm going to substitute it for W tilde, which is W of X plus epsilon eta X. And so the first, the first derivative of that is this. And the second derivative of that is this. And so now I'll go ahead and substitute that in there. So I have W double tilde, sorry, W double prime of X plus epsilon eta double prime squared plus 1/2 K. And then for W, I have W plus epsilon eta squared minus Q times W plus epsilon eta. And then I have this bracket like that, dx. And then this at epsilon equals 0 times epsilon equals 0, right? So that is what I plan to do. So now I have to take the derivative of this respect to epsilon, and you can see here that now I have to use chain rule. And so I can do that very simply. I have 1/2 times 2 times EI, W double prime X plus epsilon eta double prime. And then I have to take the derivative of what's inside now because this chain rule. And so I get eta double prime plus 1/2 times K times 2 W plus epsilon eta, because the derivative of this whole thing respect to epsilon, I have to do that a chain rule again. And now I take the derivative of what's inside respect to epsilon, that's times eta, minus Q, and the derivative of this respect to epsilon, Q does not depend on epsilon, W doesn't depend on epsilon, only this term, and so that the derivative of that is eta. And now I have to evaluate this at epsilon equals 0 times epsilon dx equals 0. And then you can see here quickly then when I evaluate this to epsilon to 0, this goes to 0, that goes to 0. So, and then I can now distribute this epsilon inside this bracket. So I get integral of x1, x2, EI, W double prime X. And now this eta double prime times epsilon, this epsilon right here, that's this difference, okay, which is del double prime plus K W del W minus Q del W dx equals 0. So that is the first version of I that I got. So what are we trying to achieve? That's the question we have here. I've done a lot here, and the question is, what are we trying to achieve? What we're trying to achieve is I have a beam, and this beam is loaded by this loading condition that's actually resting on an elastic foundation. And I have this boundary condition on the left, W of 0 equals 0, W prime of 0 equals 0. And what we're interested is in determining this deflection. Now, later on, I'll explain to you that a functional I, and I realize I use I here. So this I is moment of inertia. And I also have an I here, so I apologize for that, for using the same variable. But this variable is not the same I as that. This I here is a functional, and perhaps I can just correct it here and just make it pi and just change it to something else, right? And so I'll just change the pi for so we're not confused, right? And so what we're trying to do is find the function W, find W of X that minimizes or maximizes I, or pi. I just changed it to pi. That is really what I'm trying to do, right? So I don't want for you to lose perspective of what we're trying to do. Going back here to find the minimum maximum, you just took this derivative and find X, what X causes this function to be minimum or maximum. But that is not the question we're trying to answer. The question we're trying to answer, and the question I was answering earlier in time, is if I have 2 points and I want to find the minimum distance. Well, we know it's a straight line, but say I didn't know it. I didn't know the answer, right? So then what we're trying to really achieve was to find the one function, which function Y minimizes I, which is a functional. And for this particular problem, we showed that the functional for that looks like this. And when we took the first version of I equal to 0, we found that Y is actually a straight line. In other words, if I plug in Y as a straight line here, I is a minimum. If I plug in any other curve, so instead of plugging a straight line, I plug in a sine curve, or I plug in some squiggly line that's very long. If I plug in anything else, I is not a minimum. It will be some other value. So what we're trying to achieve then, to make sure you understand it, we're trying to find the function W. We're trying to find, it's very different. I'm not trying to find the value of X that minimizes or maximizes a function. I'm trying to find the function instead now. I'm trying to find this function W. What W minimizes or maximizes pi, which I changed it to pi so we're not getting confused with the I. So, continue. And so pi actually represents, and I'll discuss this later, and we'll be deriving that, it represents the total potential energy of this beam. And I can show you later that minimizing the total potential energy renders the system in equilibrium, and I'll be doing those derivations later on. And so hopefully that's clear. So now that I arrived at del pi equals 0, and I found that this is what I need to figure out what to do next, I have to somehow get rid of these double derivatives. Somehow I have to do that. And so that's what I plan to do now. And so the length, so I've been using x1 and x2, but say that this is at x equals 0 here, and this is at x equals L. And, you know, just to simplify it, to make it nicer, so they have EI, W double prime of X, del double X, plus K, W del W, minus Q del W, dx equals 0. That's the first, this came from the first version of pi equals 0. And I showed you how to get there. And so now I have to integrate by parts. And I can see here, there's no prime here, no prime here. There's double prime here. So I have to integrate that by parts. And let me show you how to do that effectively. So I'll have EI, W double prime X, and then del double prime. And what I've done here, what I want to keep track now is this here you put it on the left side and this on the right side. And what you're going to do next, you're going to remove one prime at a time, like so. And on the left side, you're going to increase it one time every time. So like that. So you can integrate by parts very quickly that way. And then you draw arrows like this until the very end, and then an arrow like that. And the first one is always minus, plus, the next one minus, and this plus. And this term, you're gonna have this term here at the bottom. So this term here at the bottom, right here, this times that goes back into the integral, and the other terms will go into the boundary terms. And so what I end up getting is 0 to L, EI, W double prime, plus KW, minus Q, del W. And what I did, I factored del W because it shows up here and here. And so I just factor it out just to get it done, dx. And then I have this cross term right here, which is plus EI W double prime of X, del W prime, X1 and X2. And then the next boundary term is minus EI W double prime del W at X1 and X2. And this whole thing is 0. So that's what we get. And I'll use, and then I'll invoke by the fundamental lemma of calculus of variations for any arbitrary variations of del W. And what I've really done, guys, you know, ladies and gentlemen, what I've really done is I have this beam with applied load Q, right? And that load applied Q on an elastic foundation is resting in some sort of soil here, right? That beam is going to deform. We know how it's going to deform. So that beam is going to deform something like that, hopefully. Right? So I know it's going to look something like that. That's a real solution. Say I know what the real solution is. Well, what I'm doing, what I'm saying is, hey, what if I don't know how it deforms? Maybe it deforms like this. Maybe it deforms like this. I mean, you guys know it's not true. You know, if I apply a load to a beam, it should deform like more like the red curve. But if I apply a load and I just say, well, it deforms like the blue curve. Well, that is my W, this is my W tilde, right? And this height difference becomes del W, right? So I know there's a real solution, there's a virtual function, and the height difference is your del W, right? And what I've said now then is that for any del W that I make up between x0 and L, then this integrand or this coefficient must be equal to 0. That's my Euler-Lagrange equation. And in this case, that's EI W double prime plus KW minus Q equal to 0. And then you have boundary conditions now. And you have actually, let me just do just one of them. So at X equals X1, I have natural boundary conditions and I have essential boundary conditions. And each of these has to be independently equal to 0. So for natural boundary conditions, either this coefficient here is 0, so EI W double prime at X is 0, or my other option is that W prime is known and specified. And then at X equals X1 on this boundary, I have also EI W double prime at prime equals 0, or this W is known. And then I'll repeat the same thing at x equals x2. I'll have to write this whole thing again. Okay, for our problem, where at x equals 0, this boundary was fixed. And I already told you that at that boundary, W is 0 and the slope is 0. I already gave you that condition. That clearly tells you that at x equals 0, and I called it x1, I apologize. At x equals x0, I must have these as my boundary conditions. So the boundary conditions are essential because I told you what W is, I told you what W prime is, and not only that, the function W tilde and W have to pass to the location where I actually specify the value. And so del W at that boundary is 0, right? However, at x equals L, when I look at x equals L, at this end, I'm not specifying W, I'm not. And so therefore, the boundary conditions are going to be natural, and they're going to be EI, W prime at L is 0, and EI, W double prime at prime is 0. So those will be the boundaries at that end. And because I'm not specifying W or W prime on this end, you could have a difference between this blue curve and red curve. They can be different. They don't have to be passing through the same point as I showed here. Secondly, I did make a small mistake here. That's 0 here. So I want to make sure that's 0 and it's understood. Same here, that's 0. Okay. So that's what I get for this particular problem. Okay. And so to do it, that's one way to do it. The second way to do it is to take the derivative of pi quickly. So in one shot, so pi was given as the integral from 0 to L 1/2 EI W double prime squared plus 1/2 K W squared minus QW dx. So you can just quickly in pi, you want to just identify pi as a function of W. Okay, and I'm trying to find W that minimizes or maximizes pi. Okay, and to do that, I will then just call this F. So then I have, sorry about that, the first version of pi is 0 to L, derivative of F respect to, now I see, okay, I have a W double prime and a W, so I'll take this derivative because it depends on that, plus derivative of F respect to W del W dx, set this equal to 0. You can see here quickly that this derivative is just simply EI W double prime del W double prime plus, you can see quickly this derivative here is just KW. So then comes del W, and then this derivative here respect to W is minus Q. So del W dx equals 0, and you can see that this right here is the same thing I got over here using Taylor series expansion. The next question that can come up in a particular problem is they may ask you to determine whether when I find the function W by solving this differential equation, when I solve W for this when I solve W from this differential equation, that W is the one that minimizes or maximizes the functional pi, okay? And so, but I don't know if it's a minimum or maximum. And so you could be asked that question. And so to determine that, what you need to do is examine the second version of pi, which is 1/2. And then you have this tilde here. Clearly, epsilon squared is greater than 0 and 1/2 also, so you don't have to even look at that later. But we want to just look at what is greater than 0, less than 0. And so I'll just start with the expression for pi, and remember that W tilde is W plus epsilon eta. And just to be more specific, like that. And so then I'll plug it in, and what I'll get is the following. So I have the second version of pi equals, and I will have 0 to L, second derivative of pi, and not pi, but this. I'll have a 1/2 there, of course. And then I want to now expand. So I have 1/2 EI W double prime plus epsilon eta double prime squared plus 1/2 K W plus epsilon eta squared minus Q times W plus epsilon eta. And I'm trying to find the second derivative of this with respect to epsilon. And then I have dx, set this epsilon equals 0 times epsilon squared. And then I want to check whether this is positive or negative. And so you can see here that I can expand this, by the way, really quickly. So it's W double squared plus twice epsilon W double prime eta double prime plus epsilon squared W double prime squared. And I can expand this quickly just to make it nicer. So I get W squared plus epsilon squared eta squared plus twice epsilon eta. And you can see here very quickly, if I find the second derivative of this term, that's 0 because W does not depend on epsilon. If I find the second derivative of this with respect to epsilon squared, second derivative of this, that's 0 with respect to epsilon, because if the first derivative gives you twice W double prime eta double prime, and so the second derivative will go to 0, so that goes away. And then the second derivative of this right here is going to give you twice eta double prime squared. So that should be clear. And then here, the same thing. The second derivative of this gives you 0. The second derivative of this gives you 0, and you're just left with twice eta squared. And the second derivative of this with respect to epsilon is 0 because the Q and W do not depend on epsilon. And if I find the first derivative of Q times epsilon times eta once, I just get Q times eta. And the second derivative of that again is 0. So really, at the end, what I get is 1/2 epsilon squared, 0 to L. And then I have 1/2 times twice eta double prime squared plus 1/2 times twice eta squared. And obviously this is greater than 0 because this is squared. And so that's, therefore, when we find W of x by solving the Euler-Lagrange equation, the functional pi will be a minimum. And I know that because of this. I'll now continue, and we show that by finding W, you minimize pi because this is greater than 0. So very, very good. We made great progress. And so what I want to do now is I want us to examine a 3D problem. So let's examine a 3D problem that is, I wanted to show you how to tackle a 3D problem if it were to come up. So you have a volume now, it's not a curve. So now it's a volume material, right? So there's a volume, and the volume is V, and the surface here is S, okay? And the problem statement says I have a functional I which depends on W1, and now is spatially dependent on 3 directions. And then I have a function 2. So I have actually 2 functions now. And even 3 functions. I'm going to make it 3 functions just for sake of learning. In W3. And now these are the functions. I have to find W1, W2, and W3 that minimize or maximize I. So that's a question that's been asked. And the spatial coordinates are x1, x2, and x3. So that helps you understand what is the coordinates we're talking about here. So that's what that's doing. And what I want to do, I want to define what I is. So I is, in this problem statement, is the integral over the volume of 1/2 a I comma I, sorry, no, ai comma I. So w I comma I, w k comma k plus 1/2 wi wi. And then it continues here with d. There's a d volume minus the integral of some constant b. And then we have here wk. Just give me a second. We'll just leave it like that. For the problem statement, we're going to just do it like that for now. Okay, so this is the problem statement. And so what we need to do is now determine, actually, let's just add that in. So minus bk del wk ds. And bk, and this is only specified on boundary S1. So I'm only specifying that on, so say this is a volume, V is made up, the surface S is made up of S1 and S2. And I'm only applying on part of the surface, just on part of the surface, I'm specifying this loading quantity. Remove this del, that doesn't go there. Okay, so so you may ask me, you know, there's a lot of indices, what is going on? Very simple, very simple. I is repeated, K is repeated, I is repeated. So here, what you really have, if I were to expand it, is integral of V 1/2 A. That means the summation over I 1 through 3. So that's W 1, 1. And then here, that's summation over K again. And then here is summation. That one is different. That's plus 1/2 W1 times W1, W2 times W2. Like this. Okay, so that's what we have for the functional. And so hopefully, so then I'll find the first variation of I. And the first variation of I is simply the integral, like that, 1/2 A Wi comma I del Wk comma K plus 1/2 A del W comma I Wk comma K plus 1/2 Wi del I plus 1/2 del, like that, minus, and then this is over the volume, the whole volume, minus integral bk del wk ds. B is a constant and A is a constant. Okay, so that has to be equal to 0. And I want you to notice that this is only specified on boundary S1, not on the whole surface, just boundary S1. So very, very good. And so what I want to do now is I want to remove these comma i's because they're kind of pain, you know, this comma I and this comma K are not very helpful, or I don't need them. And so, let's continue expanding here. I want you to notice how this is the same as that, so that can be added. I also want you to notice how I, comma I, and K, comma K, and I, comma I, and K, comma K, these are dummy indices. So therefore, this is equal to that in essence. So I'll just make them equal for now. So I get del I equals the integral over the volume, A, and I'll just for the sake of being clean about everything we're doing, I'll just combine it, and I'll even change the variable so you can see that it doesn't matter. Okay, so all I've done is make this equal to that because they're equal, and I changed the indices on purpose so you know that it's a dummy index, it doesn't matter. Plus, and then here, this term right here adds up straight, and that's over the volume, minus over the surface S1 bk del wk ds. And so now what I want to do is integrate by parts to remove this comma n. And that's the same as using Gauss theorem, but I want to teach you not to memorize. I don't want you to memorize that. I'd rather you learn how to do it step by step. So I have a wm, comma m, del wn, comma n. And so what you're going to do, you're taking this term here, this coefficient here, right on the left side, this coefficient on the right side, and now all I have to do is integrate by parts by removing that comma n, and then bringing it over to the other side. Okay, and so now this is, and then remember what comma m means is the derivative of that quantity with respect to xm. So that's what it means. And if I have this, then that's the derivative of that quantity with respect to m and with respect to xn. So it's a second derivative there. And so then I will draw an arrow plus a minus, but the thing I want to keep in mind is that I have a volume. Now I have a volume of material. So the boundary of a volume of material is a surface. The surface encloses the volume. And so therefore, to describe that surface, you must have a normal that describes that in hat. So what you're going to do moving forward, and let me change the variables from n to something else so we don't get confused. Let me use something we're not using. Let's use j, comma j. And I'm doing that because I'm going to use n for the surface normal. And I don't want you to get confused. I apologize for that, for making you do that. But I just don't want you to get confused. I want you to keep in mind what we're trying to do. And so the surface normal is the one that encloses the volume. So the boundary, you have to write nj because that describes the surface boundary. So then you're going to put a subscript j like that. Okay, so the first version of I then becomes, so what goes inside the integral is this term here, this times that. So it's am, not am, sorry, wm, comma mj times del wj. And then I have plus wi del wi dv, and then the surface is the boundary term that encloses the whole thing, and the whole surface S now is a wm, comma m del wj with nj as surface normal, and this is the same thing as using the Gauss theorem, but I'm teaching you not to use that. I'm teaching you how to not memorize stuff instead. So this over the whole surface, S1 plus S2, by the way. So this term is true for S1 and also it's true for S2. And then I have this term here, minus. So I have divided the surface into two pieces, and I can, because that's a total S. You can divide, you know, a surface into two pieces, and so this integral is over the two pieces, and then I have this term right here. And when I did this, you know, so we can continue now. So this is equal to 0. Okay, that's equal to 0. And what is next? So what is next now is I need to factor del somehow out of here. So I'm going to factor it using different variables. So del W, say del W C. So then I get A times WM comma MJ, and I get Kroner per delta. So I get, when I factor it out of here, I get WI del IC dV. And I'll continue working boundary terms later. And so D is equal to 0. And so now I have to apply Kroner per delta. J and J cancel, so C can come over. I and I cancel, C can come over. So then I get integral of V del WC AWM comma MC plus WC dV minus the boundary terms. These are the boundary terms. So the Euler Lagrange equation then, if I factor this out, the Euler Lagrange equation becomes this. By the fundamental for any del WC, I get AW M comma MC plus WC equals 0 in the volume V. And notice how C is a free index. So there's actually 3 equations here, 3 equations. And you can write one of them. For example, one of the equations will be A partial of W1 respect to X1. And for the first equation, you get this for C equals 1, the first equation, plus partial of W2 X2 X1 because C is 1 for the first equation, plus partial like that, plus W1. Sorry, that parenthesis ends here, and that is equal to 0. That's your first equation. And then for the second equation, just make it C equals 2 and C equals 3. So you get 3 equations as Euler Lagrange equations. And now you have to deal with these boundary terms that are here. These boundary terms need to be worked on. And so those boundary terms, the thing I want you to notice is that it's either, and then I forgot to put the S there and the S there, because that's the surface differential element, the S, right? Forgot to add that there. And so what I have now here is that I already told you that for surface S1, right, I'm specifying a value here. For surface S2, I didn't specify value of W, okay? So in other words, for S1, I didn't specify deflections. I only specified it over S2, only over S2. So on S2, we specified a boundary condition where W1 and W2 and W3 are specified. So if that's the case, then del W in surface 2 is 0, it goes away. Because W1 and W2 and W3 are specified on the surface, then del W1, del W2, and del W3 are 0. So you're only left now with this and that. So this is what we get for boundary terms. Boundary terms. So boundary terms, you get this is equal to that. Over surface 1. And I have a minus here, a plus here. This should have been plus. I apologize because there's a plus here. And this, so there's a minus here that didn't make it here. So when an integral approach, there's supposed to be a minus there that I forgot. You can see the minus here, plus, minus. And I got confused because of these marks. So let me fix that. Okay, now that's more correct. So going back, then I have this term, and then I have this term, minus BK. And that's on surface 1, that's equal to 0. So now what I can do is I can factor out del WK. I get Kronecker delta. And then what I notice is that J cancels out, K comes over. So I'm left with, by the fundamental lemma of calculus variations, again, I get AW M comma M N K minus BK equals 0 on surface S1, because on surface S2 we specified, and then on surface we specified W1, W2, and W3. So here's your ordered Lagrange equations, 3 equations, and your boundary condition is this one for a 3D problem. To answer the question, you have a volume of material. And the volume material, the question is, there will be physical problems. There will be physical problems where the volume of material, part of the surface will have you'll specify what the value of W is. And then the rest of the surface, you don't specify. So very similar to the beam problem, right? The beam problem very similarly, where I had this situation where I didn't specify what W was on this boundary, right? I didn't specify. And so, yeah, so it's just very similar, but now in 3D, part of the surface, you specify W1, W2, and W3, and I'm calling that S2, and for the rest of the surface, you don't specify anything. or you could specify something. But in this case, we just made it that way as an example. So for a 2D problem, let's consider a 2D problem. We'll study the heart behavior on the pressure loading conditions. And we're given this energy potential due to stretching of the membrane due to internal heart pressure P. And it's given us this, the expression for that potential energy. And we're asked to get the Euler-Lagrange equation. So this problem is a very good problem because it comes from a paper publication. So it's good for us to study that. So my first step is to find the first variation of E. And if I call this F, then I'll have then the integral over the surface because this is a surface over the surface. So if I call that F, then I'll have derivative of F respect to W, del W, plus the derivative of F respect to W comma beta, del W comma beta. And this is, here beta is repeated, which means that that right there, W comma beta, equals W comma 1, W comma 1, plus W comma 2, W comma 2, and so that's what we have there. And so, yeah, so that's the only thing you have really. And so all you have to do now is set this equal to 0 and just take just derivatives. So let's do that step by step. So this derivative here, there's no W here, only there. So that's minus P del W. And then this next one is a little more complicated. So that's plus sigma. And then, you know, for me, it's easier to deal with this when this is to the 1/2 power, but you guys can do this. 1/2, 1 plus W comma beta, W comma beta, to the minus 1/2. And what else I got? I got that to the minus 1/2. And also, one thing I want to mention is because there's a W comma beta here, I recommend taking the derivative against a different variable. So I recommend doing against maybe alpha or something else that was not used because beta is already being used here. And so things can get confusing. So for that reason, I'll change this. No, I can leave it at beta. It's fine. There, because that's beta right there. But this derivative, I'll take it with respect to comma alpha, W comma alpha. So then I already took that derivative and now I have to take the derivative of what's inside. So that's going to give me 1 plus the derivative of W comma beta respect to W comma alpha. So that's the derivative of what's inside. And so I have del W comma alpha. You can see here that this is Kronecker delta, del alpha beta, and this is Kronecker delta also. And you can see that this beta and beta collapse to give you alpha in there and alpha in there. So I can just continue expanding, if you will. I made a mistake because the derivative of what's inside of this, the derivative of this 1 is 0. So this should not have shown up. And notice how this is twice now. This is the same. So that's twice. And so I get W comma alpha, del W comma alpha, ds equals 0. Okay, so everything looks really good. These 2 and 2 cancel out. And now what I have to do is integrate by parts to remove this comma alpha out of there because that's not helpful to have it there. This parenthesis goes with this one. This parenthesis goes with that one, this with that one. So now the parentheses are balanced. So the first version of E will give us this expression here. I invite you to pause the video, look at what I've done. But basically I collapsed beta here, brought alpha over, and that's why you see that. And so I can then continue with this, and I want to kind of repeat the expression I have so you can see how I go about this. And I'm just repeating everything in the previous slide. And then I get this. So I just repeated everything from the previous slide over there so that I don't have to keep going back and forth. And so now I have to integrate my parts. This is a 2D surface or 2D surface. And so what I'll do then, well, it is not a 2D surface, it's a volume. So you can imagine the heart, and the heart has a thickness there, T. So this volume is really dV, which is T times ds. So the surface of this whole thing, and then the thickness is T. And so, you know, in the original problem statement, they should have put a T here for thickness of the membrane. And that way it's obvious that we're talking about a membrane there. So this is like T volume, basically. And so now I can integrate by parts. So this whole thing needs to go on the left side. And then I'll bring that comma alpha over. Plus, minus, and then I have to put a surface normal because I'm integrating a volume. Like that. And so then I get, that goes back into integral, the stuff at the bottom here. Minus. And then I'm going to try to collapse with that one. And then I have the boundary term plus. And then part of the surface you apply W, and part of the surface doesn't have the W specified. So I'll divide into two surfaces where W is specified and it's not specified. So then I have, and let me just call this whole thing. I'm just going to call this whole thing Q. So it's, sorry about that. I'll call this whole thing Q. So it's easy for me. Q times N alpha del W ds plus integral S to Q N alpha del W ds. And this is equal to 0. On part of the surface, on just part of the surface S2, we specify W, and so then del W becomes 0 on that surface. So this becomes 0 on that surface. And then I'm left with by the fundamental lemma of calculus variations for any del W, I get the Euler-Lagrange equation, which is minus sigma 1 plus W comma beta to the minus 1/2 W comma alpha, and the whole thing comma alpha minus P equals 0. And this is true in the volume, which I made it equal to TDS. And then for the boundary condition, On S2, we specified W, and on S1, del W can be whatever, because W can be whatever. I didn't specify it on S2. So therefore, on S1, Q and alpha must be equal to 0. So those are the boundary conditions. And so what I've done is covered some examples here, one on 2D and then one on 3D. And so, yeah, it is quite involved. These two come from papers, so it is good to see how it's done in real life. So I hope you have a great day, and we'll be covering functionals with constraints coming up. So I did make a mistake, so this minus doesn't go there. Let me remove that. So let's cover functionals. Let's cover functionals with constraints. So I'm given a functional I, which depends on y, a function of y, and is subjected to this constraint j. So what I want to do is now then augment and develop a new functional, I star, which is going to be equal to I plus lambda j. And lambda is a multiplier, and it could be looked at as a Lagrange multiplier. And what I want to do then is to substitute what this is in here. So I get the integral from x1 to x2 f plus lambda g dx, and I'm going to call this f star for convenience purposes. And I want you to notice how f star depends on y prime, and let me use the bracket so it's clear as a functional, y prime, and lambda dx. And so what I can do now is I can render I star stationary. So I'll find the first version of I star. And that means that this is now equal to the integral of x1 to x2. And now f star depends on these three variables. So therefore, the root of f star respect to lambda plus the root of f star. And then what I'm missing here is del lambda plus the root of f star respect to y, del y plus the root of f star respect to y prime, del y prime dx, and I'm going to set that equal to 0. Here, we need to integrate this by parts to remove this prime out of here. And so I'll do that now very quickly. So put this coefficient on the left side, this on the right side, and then remove the prime and put it on the other side. And so the bottom here goes into the integral while these terms go into the boundary term. So therefore I get integral from x1 to x2. I can factor out del y, and I have this term right here, partial respect to y minus f star respect to y prime prime. And then I have plus del lambda times the derivative of f star respect to lambda, which is g basically, because f does not depend on lambda. So I get g there, and I close the parentheses, dx equals 0, and I invoke the fundamental lemma of calculus variations, and for any del y and any del lambda, then the parentheticals becomes equal to 0. So then I get partial f star respect to y minus the derivative of this, and that's for the variable del y. And then for the variable del lambda, I have the integral from x1 to x2 g dx equals 0. So that's that constraint, that very constraint I recovered by applying calculus of variations. So I get the, and then I want to remind you that I do have a boundary term from this cross term here. So that's plus boundary terms, which I'm going to neglect talking about it now. So in essence, what I want to show you is what we've done, but typed up. So I have a functional I, and this functional I here is constrained to J. And so what I'm going to do is create a new functional I star with a Lagrange multiplier. So again, this is a functional I that I'm subjecting to J, and I'm creating a new functional I star. And so I have F plus lambda G, and F star here depends on Y, Y prime, and lambda. And then I'm going to take the first variation of I star, and since F depends on Y, Y prime, and lambda, then you can expand it like that. So what I want to do now is integrate this by parts, which I already did here. When I do that, I'll get this. And by the fundamental level of calculus variations for any del Y, this must be equal to 0. And for any del gamma lambda, the integral times this is equal to 0. And we're able to then accomplish what we were looking for. Since in our case, we're going to specify the boundary conditions, so Y at x1 and Y at x2 will be specified, then del Y is 0. And so this goes away in the boundaries. That's only if I specify it. I'm going to specify for this particular example. So this is what we got. And by the fundamental lemma of calculus variations, you get your first equation, and then you will get your constraint naturally, which was already given. So what if I want to then solve the problem of maximizing the area under a curve of specified length S? So I'm given 2 points, and then I'm given a chord, some sort of chord that has length S, and you know how to calculate the length, and I'm providing that length. That length is L. I'm giving it to you. The question is, how do I get the maximum area? And if this is Y of X and this is X, the area is the area under this curve. So if I want to maximize the area, I definitely have to then take a little slice of dx. This height is y. So then dA becomes y dx. And so the area becomes from integral x1 to x2 y dx. And so this becomes the area of interest. And I want to maximize this area. Given this constraint, given this curve length, I'm giving you the length, not telling you the shape. We need to find that shape that maximizes this area. So that's what the question is asking for, is maximize this area subjected to this constraint here, which is a curve of a constant length S. Okay, so that's what this problem is about. And so we can derive that fairly quickly. So let's go through a derivation here. So area in our case is x1 to x2 y dx. S equals integral x1 x2 square root of 1 plus y prime squared dx. And so now I'm saying this is a constant. So S is fixed. So now I'll augment the functional by adding a lambda Lagrange multiplier And so when I do that, I get I star, which is what I discussed earlier. I star is A plus lambda times S, which is the integral of x1 to x2, y plus lambda times the square root of 1 plus y prime squared, right, dx. And so now I'll take the first variation of I star, and I want you to notice that here, this is f, and f depends on lambda, y, and y prime dx. So the first variation of I star is going to be equal to x1 to x2 partial of f respect to y del y plus partial of f respect to y prime del y prime plus partial of f respect to lambda del lambda dx. And so that's equal to x1 to x2. And so now all I have is this derivative here, which is 1. And then this is easy to find the derivative with respect to y prime. That's simply lambda, and you can do it fairly quick, is plus lambda y prime like that, del y prime. And then you have the constraint, which I'm going to call plus lambda del lambda s dx equals 0. And so the constraint equation is known. I can now determine by integration by parts, I'll remove this y prime. I want to do that. When you do that, the Euler-Lagrange equation and we can do it really quick here. So I have lambda y prime 1 plus 1 y prime squared, and I have this del y prime. I can remove the prime and put it over here. Plus minus, okay? And so now the del I star becomes integral from x1 to x2, and I have 1 minus, and then I have lambda d dx y prime square root of 1 plus y prime squared and plus parentheses. And I can add the Lagrange multiplier, no problem. That's also showing up, plus s del lambda. I could do that. Dx equals 0. But I'm not going to focus on that. The important thing is that this is multiplied by del y. And so by the fundamental lemma of calculus variations, for any del y, then the Euler-Lagrange equation becomes 1 minus lambda d dx y prime square root of 1 plus y prime squared equals 0. So that's the good news, and I want to show you what happens now. So this is my Euler-Lagrange equation, and you know, some interesting things will happen now. So the augmented functional gives us this. I showed you that, and I also had the boundary conditions, which I did not discuss in extensive detail, but this boundary goes to 0 because in the example problems I'm giving you here in this case, I am specifying the location of these 2 points, and I'm just giving you a chord. And we need to just find the shape of that chord that maximizes the area under this, under here. Given that length, this length is given to you as S. And so, yeah, that's what we found as Euler-Lagrange equation. This is what we found. And so we should be able to then integrate. We can quickly bring the 1 to the other side of the equation and start solving this differential equation. So you can bring this 1 to the other side, divide everything by lambda, And I could do it really quickly here to show you. I'll divide this by lambda, and then bring, this becomes 1 here, bring this to the other side of the equation, and then integrate once. Okay, so I'll integrate once. And then once I integrate once, I get this expression. Okay, and we can solve this by solving for y prime squared. So you have to square both sides to do that. And once you square both sides, this is what you get. And then you can take the square root of this, which I show you in the next slide. And then you can integrate it once to get this. So with a new constant. And then equation 9 can be rewritten as this. But this is the equation of a circle and is centered at C1 and C2, and interestingly, you have a lambda here. And so you can actually even pursue now, like if I were to give you these endpoints, you can get fancy and try to solve for that. So you can, given these boundary conditions, you can solve for this. You can solve for C1 and C2 fairly easily. And in this example, you know, I specify 1 and 1 here. And the length that was given in this example problem was this. And so you can then find C1 and C2, and you can find even the radius of this circle. And the radius of this circle becomes the Lagrange multiplier, interestingly. So given this length, the lambda can be found to be that. And it makes sense that the circle is the one that gives you the max area